are very beautiful. Yes, they are. Well, if they could be made of iron, they would be more durable. Ships made of iron? It's impossible. Look at this. Wood. Wood floats on the water. Iron. Iron sinks in the water. See? Wood floats, iron sinks. A ship should be made of wood.
I don't think so. In ancient Greece, there was a great scholar, Archimedes. He discovered the phenomenon of flotation, and that the weight of an object is reduced when placed in the water. I think that a ship made of iron can be made to float by the displacement of water. Therefore, I believe that iron can be used to make a ship.
No, I disagree. A ship should be made of wood.
They can't agree. The first person came to his conclusion by observing similar phenomena from daily life. The second man, he made a deduction based on established scientific phenomena. Which one is correct? Well, I hope by now you all know.
Listen, the boss says the average score of these 5 candidates for the test is 90. He wants them to attend an interview.
All right, let me see what each of them scored. 91, 91, 90, 90.
Hold it. Can you guess what the last score is?
Sure, that's really easy. It's 90, right?
Are you sure?
Certain.
All right, class. The young lady guessed the score at 90. But was she correct?
Let's take a look then.
In fact, she made a very common mistake. She took the marks from the first 4 papers and then concluded that the 5th number should be 90. Her mistake was that she didn't use the concept of average value to work out the number. What is the sum of the 3 interior angles of a triangle? Of course, a protractor can help us measure them, but they're still approximate. There are errors in the measurements. This can mean that the data is not accurate. This, in turn, will make any conclusion drawn also inaccurate. A conclusion deduced from established principles will be all the more accurate. This process of deduction from established principles is called deductive reasoning. Around 300 or so BC, a Greek by the name of Euclid used this method of deductive reasoning to develop a framework of geometry. This systematic framework of geometry is known as Euclidean geometry. And his book, Elements, has a major influence in mathematics. If we want to build a wall, we first build a solid base layer. Then we add a second layer on top of that. Then, when the bottom 2 levels are firmly set, we add another layer until, layer by layer, we have built our wall.
Hey, would you tell me something about Euclidean geometry?
Sure. What Euclid did was just like building a wall. You see, in Euclidean geometry, the foundation layers are definitions and axioms. Definitions are descriptions used for describing mathematical facts.
Oh yes, like a parallelogram is a quadrilateral with 2 pairs of opposite sides that are parallel. That's the correct definition, right?
Yes, that's right. Now axioms. Mathematical facts that are obviously true. For example, if B equals A, and C also equals A, then B and C are equal. This is a mathematical fact that is obviously true and which does not require any proof. This one's called the axiom of equality.
Well, what about the wall's second level?
The second level is the results deduced from definitions or axioms in the first level. These are called theorems. There are some in elements. One is very well known. It says that the sum of adjacent angles on a straight line is 180 degrees. Using this axiom and the axiom of equality, we can deduce a theorem in the second level. Vertically opposite angles are equal. Book Elements, there's yet another axiom. Corresponding angles of parallel lines are equal. Using this axiom and the theorem of the equality of vertically opposite angles that has been confirmed, we can deduce a theorem at the third level. That is, alternate angles of parallel lines are equal.
And I think I know how. X equals Y. Because they are corresponding angles of this pair of parallel lines. And here is the axiom. In addition, x is equal to z. Because they are vertically opposite angles. And here is the proved theorem. According to the axiom of equality, y equals z. Therefore, the theorem is proved. Alternate angles of parallel lines are equal.
Thanks a lot.
You're welcome.
With this theorem, we can deduce using parallel lines that the sum of the interior angles of a triangle is 180 degrees. I'll give you a few hints. Understand now? Euclidean geometry is built up on a step-by-step basis.
Oh!
Deductive reasoning is very similar to building a wall of blocks. If the lower levels are not fixed properly, the upper levels will be unstable. In deductive reasoning, if a first deduction turns out to be incorrect, then all the results will be unreliable.
Right. But what do you mean by an incorrect deduction? Do you have an example?
Here's one. Look here. The diagonals of a rhombus are mutually perpendicular to each other. By applying the reverse reasoning, is it equally correct to say that a quadrilateral with mutually perpendicular diagonals is a rhombus?
No, that's false. A quadrilateral with mutually perpendicular diagonals may also be a kite.
Of course. It's just like saying that the ground is wet after it has rained. But when the ground is wet, it may not be due to rain. Similarly, if a theorem's carelessly used in reverse, it can make the deduction incorrect.
But still, there are theorems where the reverse statements are true. For example, alternate angles of two parallel lines are equal. Its reverse statement, when the alternate angles of two straight lines are equal, the lines are parallel, is also valid. It works both ways.
That's right, but its validity must be proved. And then, once it's proved valid, well then, this reverse statement becomes a theorem in itself. It becomes the converse theorem of the original theorem. here's a geometrical problem and some steps to its proof. Can you arrange the steps in the proper order for proving?
I'll try. P and Q are the centers of two circles. The circles intersect each other at R and S. PQ and RS intersect at T. We need to prove that RT equals ST. Now, what's going to be the first step? This is the center, so this is a radius. Radii of the same circle are equal. Therefore, PR equals PS. QR equals QS.
So what can we do with these two equal sides?
We can use them to show that these two triangles are congruent. PQ equals PQ because they are common sides. Therefore, triangle PRQ and the second triangle PSQ are congruent. The reason is side, side, side.
The way you're proceeding is exactly the way Euclid proceeded. You're deducing results from given conditions and theorems.
It's deductive reasoning.
That's right. With a geometrical proof problem, you need a clear target. From here, you can work backwards. Every step can be traced and each one put in order.
Oh, right. So in this example, we can work backwards from the final result. That way, we see if we can use the congruent triangles. In fact, our target is RT equals ST. RT and ST are the corresponding sides of the two triangles. If we can prove that these two triangles are congruent, then we can use the reason corresponding sides of congruent triangles are equal. Now to prove these two triangles are congruent, there, we can make use of the result that triangle PRQ and triangle PSQ are congruent. Therefore, the reason for the congruence of the two triangles is side, angle, side. All right, now I understand.
Great detective work. Yes, deductive reasoning can train our brains to think systematically and also enhance organizational skills. Many mathematicians develop their interest in maths at secondary school through their eager solving of geometrical reasoning problems.
This problem takes time to solve, and a lot of effort. I believe that the learning and the interest in it are things that come simultaneously.